So of course, you guys are the only ones that get this for coming to class. No, I'm just kidding. I uploaded this underneath the Unit 1 OChem review module. The other thing that I uploaded under our Unit 1 OChem review module, I believe I did this after our class on Tuesday, was something that I had been promising you I would upload but hadn't gotten there yet. Sorry, I'm going to take a short twist. First, the functional groups table. I updated this. So it now has nitriles, cyano groups. I swear I added something else, but it doesn't stand out to me what else I added from the old version. So if you downloaded that on the first week, you might want to download it again. Yeah, I added the nitro group. I didn't have nitros before, but we'll do nitro quite a bit. So under that Unit 1 module, you could just sketch them in. Unit 1, reviewing first semester organic chemistry. I know it looks a little different on my end because it's got color, but these four, this is my OChem 1 midterm and answer key, OChem 1 final and answer key. So you want to test your knowledge from OChem 1, try to take that midterm, try to take that final, and then look at the key and see how well you did. Not a bad idea. Then what you see underneath it is the OChem 1 review. That is your active assignment. How many of you have started the active assignment? Great. Going well? Okay.
Where do you get it?
Active? Oh, you have to get it on active. Okay. Underneath that, OChem 1 written work. Who has started their OChem 1 written work? Oh, nice. No one. This, in my opinion, is much easier than active because all of the OChem, all of the written work assignments that you'll have this semester, there's only a handful. They're one page. It's like, I think this is 3 problems that you have to solve, totaling 10 points, maybe. And the other ones are 2 problems that you have to solve.
When is that one actually going to be due? It still says May 29th.
No way.
There's still a list of
June, July.
That are due in like May and June.
But I changed them all. Well, thanks for pointing that out. I told you guys I'm taking a course this fall as well. And I had to point that out to the instructor of that course, that we couldn't do the assignments because they were past due and locked. Okay, so all the active assignments are due correctly. It looks like the PLOs and the written works are not done correctly. So I will edit those tomorrow, if I remember to. But if you can send me a message, I will definitely remember to. And that will make it a lot easier. Okay. So you guys know where to find this. Those of you that are watching the recording, you know where to find this. I guess I kind of got away from it. This handout that should help you apply your reactions from OChem 1. They are down here, OChem 1 practice reactions. I don't have a key for it yet. I might make a key. But if any of you are interested in, like, I think I could make a key for this, send it my way, and I'll proof it and post it if you have it all correct.
Yeah, it's blank on mine.
Love that. All right.
It might just
yeah. You know what I'm going to do is remove the doc, and I think that's what the issue was, and I'm going to upload the PDF. Because that's just terrible.
Word is worse.
You know what I think it is? Word on my Mac, which is where I make the molecules and the reactions, doesn't upload well into Word on my PC.
I feel like there's something weird with Word on Canvas too.
Yeah.
Like whenever I try and pull a Word doc off Canvas, it's like all over the place.
Oh yeah.
So I have to like convert it to PDF to feel like I'm actually seeing what I'm supposed to see.
It's terrible. So, is this graded?
No.
Is this due? No. This is a supplement. And if we have time in the next couple of weeks, I mean, this class period or next week, maybe we'll be able to go through some of these together. I do know there are a few reactions that are left off, but it's really challenging to fit them all on there. And I feel like they were already covered well enough, so it's a pretty thorough review. All right, any questions on where we left off last week? Matt?
I actually just have a quick question on the unit tests.
Yes.
So there's the part A and the part B. Can you just explain how those work again? Because I'm a little confused.
Absolutely.
Try it again.
Part A is a multiple choice test. Part A, you have 2 attempts. Your first attempt, you'll see your responses and the ones that you got correct and wrong. You won't see the correct answers for the ones that you got wrong. My goal with giving you 2 attempts is to allow you to master the questions you got wrong. Remembering that those questions pull from banks, question banks. So the second time you take part A, you may get some repeat questions, but you will almost certainly get new questions for some of them. Which means you'll have to not just figure out the correct answers for the ones you got wrong, but master that concept when it shows up in a different form. Part B is a short answer portion. Because your midterm and exam requires you to draw things by hand, I want to see you draw things by hand on your unit test, so I can catch it and give you feedback before you come into the midterm and the final. Additionally, your written work is meant to be due, and I am going to change that due date to next week, Thursday night, so that I can grade it Friday. Your written work is meant to be due before a unit test, so that I can grade your written work before you go into the short answer of your unit test. Again, I want to give you feedback on what you're putting to paper before you put it to paper on the unit test, and I'll give you feedback there again before you put it to paper on the midterm. So it is meant to be scaffolded. Written work lets me get that first catch, point you in the right direction. Unit test steps it up where you have a time constraint, and I can still give you feedback. And then the unit test, of course, the tightest time constraint and the highest stakes. Did that clarify it well enough? Great. 1 attempt at the part B because it's short answer. All right. Any other questions before we dive back in?
Was it
Cameron?
only the unit tests and obviously the midterm and the final that don't apply to the late work policy?
Correct.
Everything else is free?
I will take written work until the final exam. I will take active homework until the final exam. I will take the analysis of the organic compounds until the final exam. But it's not going to do you any good to push them off, right? Because if I can't give you feedback on your written work, then you go into the unit test without any feedback and without any idea of how to do those mechanisms.
I don't plan on it. I just want to make sure it got
Yep.
done.
You got it. Awesome. Oh, I think there's one type of assignment I never talked much about. These are program learning outcomes, PLOs. Our accreditation body, the people that say, Salt Lake Community College, you are good at your jobs, they want to know that we are checking how well our students are meeting the learning outcomes of our chemistry program. So all sections of a course have to administer the exact same assignment that can be used as a reference. So you guys that have taken labs before here, you've already seen some assignments that say PLO. That's where we dip in and check that you guys in all of the lab sections are meeting our learning outcomes. Because the organic chemistry classes are all very individual by the professors, these are the reference assignments. They're made by the course lead. That means they do not look like my material. And they will not reflect your unit tests. They will not reflect your midterm or your final exams. They are graded for extra credit to incentivize you to do it. But you will not hurt your grade by getting things wrong on it. You're required to do it, and you get bonus points for it. So that's kind of the weird part is I'm incentivizing you to do it by giving you the extra credit. So do it because it cannot hurt your score. It might feel different. It might feel like listening to a different dialect of a language because it doesn't look quite like what we're looking at, but it will be useful.
You have to do the entire thing to submit it for the extra credit point?
No. You can totally pick and choose parts of it to do if you want to. I don't know if that would be the most beneficial, but you would just get partial credit for it then. Absolutely. Okay? Cool. On that note, do you guys know how close we are to the unit test? Yeah.
We haven't even learned any.
I know. We haven't done anything. So how are we on the 4th day? And we haven't talked about anything yet. So we've got a lot of ground to cover. Do you remember where we left off on Tuesday?
Molecular orbital theory.
Yeah. So we had discussed bond line assumptions, right? We said we're using bond line theory because it simplifies things, but we had to agree to some assumptions. We can assume carbon. We can assume hydrogens bonded to carbon. We can assume lone pairs. We cannot assume heteroatoms. We cannot assume their hydrogens. We cannot assume. Correct. For mechanisms, you must show relevant electron pairs. But in just a generic bond line structure, we cannot assume formal charges. So, assume carbons, assume hydrogens bonded to carbon, assume lone pairs if you want to. Do not assume hydrogens on heteroatoms, do not assume heteroatoms, do not assume charges. Good. Now, bond line or valence bond theory is basically what we follow when we're looking at Lewis dot structures. This is valence bond theory. So I had this molecule alanine up here earlier. Valence bond theory tells us a couple of things. One, how many pi bonds are in alanine?
One.
Just one. Here between C and O. That's very easy to figure out from bond line structure, which is what valence bond theory basically asserts. How many sigma bonds are present? Oh, this takes a lot longer. And some of you on my OCHEM 1 midterm missed it because you counted all of the clearly indicated ones. But you need to get in there and count all of the assumed ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigma bonds. Anybody get a different number than me? Now, beyond that, valence bond theory asserts the nature of those bonds. So this pi to pi bond is the result of a p to p orbital overlap. Pi bond equals p to p orbital overlap. But then there's this sigma bond between the carbon of the carboxylic acid and the adjacent carbon. Yes, sir?
Isn't that carbon with 4 bonds hybridized?
This carbon is sp2 hybridized, which means it has an unhybridized p orbital that overlaps with the unhybridized p orbital of the oxygen. Looking at this carbon-carbon bond, I have an sp2 carbon and an sp3 carbon. So the sigma bond that they have is the result of an overlap between an sp2 orbital and an sp3 orbital. Then I can look at the sigma bond caused by the overlap of this carbon-to-carbon bond. What orbitals overlap to give me this sigma bond? sp3 to sp3. Lastly, what about the sigma bonds between the nitrogen and the hydrogen. Someone raise your hand and tell me what orbitals have to overlap for a sigma bond between nitrogen and hydrogen here. You want to raise your hand?
Oh,
Yes, Kevin.
SP2.
No. Anybody else? So sp2 is just one orbital. You gotta give me two. Jacob?
The sp3 and s.
Good. Hydrogen only has an s orbital. And the nitrogen here is sp3 hybridized.
Because the lone pair is an orbital.
The lone pair is in an orbital of its own. You're right. James, you've got a confused look on your face. Any-
I forgot about the one pair.
Okay, so you were also looking at the nitrogen and thinking that it was sp2. Okay. Good review then on just remembering how to figure out hybridization. Here's a good tip for you, James. How many pi bonds going to the nitrogen? Then it's probably sp3 hybridized. Because the only reason that atom is not going to hybridize all four of its valence orbitals is if it needs a p orbital for a pi bond, or two p orbitals for two pi bonds. Valence bond theory is the one that kind of makes sense when looking at a bond line structure. Do you guys have questions on valence bond theory? You need to be able to determine hybridization of the two atoms involved in a bond. And now you have your valence bond theory overlap.
This is just a guess on how atoms bond.
It's not necessarily a guess so much as the connection between their hybridization and the fact that they have a bond. Molecular orbital theory, also called MO theory, it becomes more challenging to look at a molecule as a whole. Computational chemists, physical chemists, they do this kind of stuff all the time, looking at how orbitals span across entire molecules. But for the context of our class, we're going to look at individual bonds between two atoms or conjugated pi systems. So I want to start you off at the basics, because I know some of you came from professors who don't think MO theory is useful, and I shame them, don't worry. Let's look at hydrogen bonding together to become H2. I'm just kidding, I don't shame those professors, but I do believe that there is useful information in MO theory. Hydrogen atoms, we will be plotting energy along our y-axis. This is an MO diagram. On the edges, we are putting the atoms that are coming together, and in the middle, we're putting the new orbitals that result, that are not atomic orbitals overlapping, but that are now new mathematical equations, similar to hybridized orbitals, that come together from the summation and subtraction of the two atomic orbitals. Hydrogen has a 1s orbital. When these 1s orbitals come together, those spheres can either be in phase with each other. Mathematically, this lowers the energy of the new molecular orbital, which now spans two nuclei. These are my two little nuclei. It's not a weird smiley face.
The oval S, is that the oval S combined shell?
Yeah, it does look more oval.
Now what does in phase mean?
It means that the mathematical equations that describe them, excuse me, either both start with plus or both start with minus.
Would physicists know what it means?
I just told you what it means.
You said that well, the math came from the observation of the electrons. So they have an actual relationship going on that we just can model.
When these orbitals are out of phase with each other, when these mathematical equations start with plus or minus, one is shaded, one is unshaded, they actually subtract each other from the middle, and we get this two-edged or two-lobed orbital that has this gap in the middle, and again, the nuclei are sitting right here. It's one orbital spanning this new molecule. Notice that it's a molecule and not a compound, right? H2. It's a new orbital that is not atomic orbitals, but molecular orbitals. The out of phase combination is a higher energy mathematical equation. Now remember that each hydrogen brings one electron. So now these electrons move to the lowest energy orbitals. That is, they'll both move to the bottom orbital here. If anybody can get me IT, I can't get this thing to stay on for more than 5 minutes. A little bit of terminology about these orbitals. It's not terms that we'll see a lot, but they are useful to know. MOs come in two primary flavors. This is the highest occupied molecular orbital. We call it the HOMO. It is the highest energy electron orbital that has electrons in it, highest occupied. And this is the lowest unoccupied molecular orbital, the LUMO. If electrons will be used from this molecule, they will come from the HOMO. If electrons will be accepted by the molecule, they will go into the LUMO. Without having to build the entire thing, I'd like to show you why this is a little bit relevant in a way that isn't necessarily organic chemistry yet. If you look at molecular oxygen, O2, you all probably know the Lewis dot structure of O2. And you would say it has a sigma bond, a pi bond, and two lone pairs each. But the MO diagram of it, wow, that is really grainy. The MO diagram says that it actually has a sigma bond that is canceled out by a sigma antibond, and then a sigma bond, a pi bond, and then a net pi antibond. I want to say that one more time. MO theory suggests that oxygen has two pi bonds plus an anti-pi bond, which sums to give you one pi bond. Lewis dot structure says just one pi bond. MO theory says it's not that simple. MO theory also says that there are these electrons here that are not paired. Lewis dot structure does not say that. The Lewis dot structure suggests that every electron has a pair. And MO theory says these electrons are unpaired. And what is an unpaired electron? It's a radical, and it's a magnet. So when you super cool oxygen and you make it a liquid, it has magnetic properties because it has unpaired electrons. Then again, you give oxygen enough energy and it can overcome those magnetic attractions, which is why you can't magnetize oxygen in the air, but you can magnetize it with low enough temperature. MO theory explains way more than a Lewis dot structure will. A couple of other terms I want to put up here.
What's an antibond?
An antibond is electrons in an orbital that result in higher energy than the atoms being separate from each other. So for instance, H2 is stable because the electrons are lower in energy together than they are separate. But He2, diatomic helium, is filled the bottom and the top orbitals, which means net cumulative energy, it's equal to being separate. If you could take two helium atoms and bond them together, they would not know that they are bonded, and they would just drift away.
So it's like constructive and destructive interference of waves, right?
Correct.
So like, how come then if you have constructive interference on the bottom one, making it a better wave,
Mm-hmm.
why does a one destructive interference wave, which is ends up bottoming out, why would that affect the rest of the bond?
No, I missed what you're trying to get at. If I occupy this constructive interference wave, it's lower in energy. It's harder to break it apart.
Why is that lower in energy if destructive interference bottoms out the waves?
No, constructive interference,
Destructive bottoms it out.
it neutralizes them.
So why would that be higher in energy?
I don't know. We'll have to consult a physical chemistry textbook for that. I've got one in my office, so swing by.
I'll give it a look.
All right, a couple of more terms that we say. When you have that head-on overlap, this orbital is not an SS orbital overlap. This orbital is not S. This orbital is not sp2, sp3, sp. It's not p. This orbital is sigma. It is not an atomic orbital. It is not a hybridized orbital. It is a molecular orbital. So it has a new name, similar to how hybridized orbitals are not atomic, so they have new names. That is the lower energy bonding orbital. The anti-bonding orbital is called sigma star.
Is the bottom and a nucleophile and the top an electrophile? The hydrogen gas?
In a way, so if H2 is to act as a nucleophile, this is where the electrons come from, the highest occupied molecular orbital. If H2 were to act as an electrophile and accept electrons, this is where the electrons would go, into the LUMO. Let's take a look at sp2 hybridized carbon bonding with sp2 hybridized carbon to give me a carbon-carbon double bond. Can you tell me, and feel free to look back in your notes, what orbitals do these sp2 hybridized carbons have available to them?
Three sp2s and a p.
Perfect. 3 sp2 orbitals and p. Which is higher, the 3 sp2 orbitals or the p?
P.
How do you know?
Because I've been told that p orbitals are higher, or that hybridization lowers the energy.
So p orbitals are higher than s. If s hybridizes with p, those will fall somewhere between s and p. So a leftover p orbital will be higher in energy than the 3 sp2 orbitals. A word to the wise, I always cram myself in here, and I always wish I could give myself more space. So feel free to space this out a little bit. Now, these sp2 hybridized carbons, they're not just bonding to each other with all of their orbitals. I think you would agree that they have other bonds going to other things. And those utilize hybridized orbitals. Those are sigma bonds. So we're going to ignore 2 of the sp2 hybridized orbitals because they won't be relevant here. Deal? And carbon, being a tetravalent atom, has 4 valence electrons. So I can put 4 valence electrons in on each side. Just so you guys realize, I'm putting 1 carbon spin up and 1 carbon spin down because eventually they'll need to pair, spin up and spin down. That much is arbitrary. Head-on overlaps. those that result in sigma bonds, they have very good constructive interference. They overlap quite a bit. That means they also have very good destructive interference. They overlap quite a bit even when they're out of phase. So this sp2 orbital overlap goes very high and very low. And it creates sigma and sigma star. As a reminder, the sp2 orbital looks like this. Two lobes, one that is bigger than the other. So when they come together constructively, it looks a little goofy. You've got this big oval with little ears on the side. And again, the two nuclei fall somewhere in there. When they come together destructively, you get what looks like two sp2 orbitals that are out of phase and pointing opposite each other. And again, the nuclei lie somewhere in here. I hope that what you can see about the destructive orbitals is that they look like each nucleus has its own orbital, because that is what you should be seeing. That would mean if electrons occupy that, those atoms won't even know they're bonded. It's almost as if they both have electrons in their own original orbitals. Anti-bonding.
Are the nucleuses in the crook?
Yeah, you know, the nuclei are probably closer to these nodes, but that's not what I don't think that's what adds to your understanding as much. Let's look at what happens when the p orbitals overlap. Because p orbitals are smaller in size, they don't overlap quite as well. And this means that they don't get as much constructive interference, and they don't have as much destructive interference. So p orbitals create pi orbitals, and pi star orbitals, which always fall in between sigma and sigma star. Not quite as low, not quite as high. And it's because their orbitals don't overlap quite as much. A p orbital looks like this. So when I have two p orbitals that come together, I will be honest, showing the new molecular pi orbital looks a little goofy and is a little hard to draw. So a lot of times, we'll just draw what looks like two p orbitals pushed right up next to each other. To be fair, there would not be this line down the middle. That would just be one lobe. But it's easiest to show it this way, especially when we get to really long chains. What I want you to pay attention to is the fact that they are in phase, shaded together, unshaded together. Pi star, they should become out of phase. And if we were doing this realistically, they actually create this kind of butterfly wing effect because the overlap in the middle gets subtracted and what's on the outside kind of pushes out. But again, not as important as showing they're a little bit farther away from each other and they're out of phase with each other. Like this. Pretty little butterfly. Now, where are the electrons from each of the individual carbons going to go? Keep in mind that these two electrons on both atoms, those are taking part in bonding to other groups. I only have a pi electron and a hybridized electron, and a pi electron. 4 electrons for this diagram, they need to fall to the lowest energy. 2 to sigma creates a sigma bond between the two atoms. 2 to pi creates a pi bond between the two atoms. I've consumed all of my electrons. This is my orbital. Luis, can you tell me which orbital, sigma, pi, pi star, or sigma star, is my HOMO?
Sigma.
No. Remember what HOMO means?
It's the highest occupied molecular orbital.
Highest occupied. How many of the 4 are occupied?
Uh,
2. Which is the highest in energy?
the pi bond.
Good. This is my HOMO. So if this alkene, if this carbon-carbon pi bond is going to do something with its electrons, will it use its pi electrons or its sigma electrons? Pi electrons, because they are the highest in energy. If any electrons are seeking a lower energy home, it's the highest energy electrons, the electrons from the HOMO. So remember, HOMO, electrons come from here. Pi bond breaks before the sigma bond. Does Lewis dot structure tell you that a pi bond breaks before the sigma bond? No. You just have to know it. MO theory tells you that a pi bond breaks before the sigma bond. Cooper, which of these 4 orbitals is my LUMO? This Good. This is my LUMO, my lowest unoccupied molecular orbital. Now remember, if another chemical species interacts with my alkene and has high energy electrons to donate, it wants to donate them to the lowest energy orbital. We always fill from lowest energy up. So which bond, sigma or pi, would break first if this species accepted new electrons? Pi bond breaks first because pi star is the lowest unoccupied MO. It is the one that accepts electrons, breaks the pi bond by nature of being a pi anti-bonding orbital. Remember I showed you oxygen and said oxygen has 2 pi molecular orbitals that are filled plus an equivalent of 1 pi anti-orbital that is filled, which sums to give you just 1 pi bond. If I occupy LUMO, I break a pi bond. If I steal from HOMO, I break a pi bond. Which bond breaks first in an alkene, pi or sigma? Pi, no matter which way you look at it.
So when we're saying something's higher or lower energy, is that being caused by the nature or the shape or the geometry of those orbitals coming together? Because something's going to be higher energy if you have, I mean, are we thinking like magnets here where we're going to have higher energy because the nature of that orbital has 2 like signs closer to each other more of the time? Does that make sense?
I'm not sure if I'm tracking, so let me see if I'm answering it right.
I'm just wondering, I guess to make that simpler, like what makes it higher energy versus what makes it lower energy?
Yeah.
Because what I see there in that bottom sigma is almost the electrons spending more time in the same sign. Am I misreading that?
Okay, so you're thinking like, because I've got this one lobe that's really large, that lowers the energy.
That lowers the energy, but does that mean that, because we're saying those lobes are just mathematical equations, right?
Yeah.
And the mathematical equation is the sign.
Has a sign. The mathematical equation has a sign.
Okay.
Minus, plus, minus. For instance, if you have a wave in a pool, you can see parts where the wave is actually going down before the wave goes up. So that would be a mathematical equation that says subtract this intensity, add this intensity. Yeah? So you've got a mathematical equation describing the electron here, where in these two regions, it follows the equation with minus, and in this big region, it follows the equation with plus.
So that does not equate to two positive ends of a magnet spending time next to each other.
Correct. It does not mean two positive ends of a
Different
magnet.
concepts.
Correct.
Okay.
Electron orbitals are not the north and south of magnets.
Okay.
Yes. Electron orbitals are their wave function, which is different.
Why is there north end of a magnet?
I don't know why they picked north. Now, do you guys understand why I've shown this? I want to try and make a point out of this. In OChem 1, we learn about the halogenation reaction. And we say that the alkene acts as an electrophile. And I kind of contest that because there are several things that happen at once. The alkene attacks one of the halogens, and at the same time, the halogen uses a lone pair to attack back. And in that instance, the other halogen is kicked off. And this gives us a halonium ring and a halide ion as products. Courtney, can you tell me a bond that is broken in this step? And describe the bond as best as you can.
This is the first time I'm learning in depth about any of this.
That's okay.
So I'm guessing a pi bond is broken.
A pi bond is broken. Can you tell me what atoms were pi bonded?
The carbon.
Good. A carbon-carbon pi bond breaks. Perfect. What else breaks? Where? A bromine-bromine sigma bond forms. Can you tell me, or breaks? Can you tell me what bonds break, Kayla? Or sorry, form.
Form?
Can you tell me a bond that forms?
Sigma
Where?
between the, or two between the carbons and the bromine.
Good. Two sigma bonds form. All right, so looking at an MO diagram or projecting molecular orbitals onto this, I want to show the breaking and the formation of some of these bonds. The bromine-bromine bond that breaks is a sigma star orbital being occupied. So here is that sigma star orbital. Notice how it spans the molecule, and it has those out of phase, oops, this should be shaded. It has those out of phase lobes.
How do you know?
Because it needs to break. We said the bromine-bromine bond needs to break, which means its sigma star bond, its sigma star orbital needs to be occupied.
Are half the bromines in the universe like this, and the other half are the sigma?
No. This is just a mathematical equation that these two bromines have. Now, where are the electrons that are going to go into them? It's the highest energy electrons, the HOMO electrons from the alkene. And their orbital, I said it looks a little funky. Oops. Their orbital looks like this. It looks like one big fat p orbital. And of course, this is the carbon-carbon double bond. The HOMO electrons are going into the LUMO orbital of bromine. Does that make sense? The HOMO electrons from the alkene bond is breaking. Its electrons are leaving. They're going to break the bromine-bromine bond. Now, at the same time, bromine is giving electrons back. Well, if bromine is giving electrons, what orbital will they go into on the alkene? Where do electrons go on this alkene? The LUMO, which is what? The pi star. So I'm going to draw this again because I can't draw that many orbitals in one place, and I'm going to draw the pi star orbital, which looks like out of phase p orbitals. Now for bromine to donate electrons into that orbital, it needs to have orbital overlap, which means it's going to have two regions. One that is unshaded to match with the unshaded region, and one that is shaded. And then, of course, here is the bromine. What does that orbital look like? It looks like a p orbital. Now, I know that you were probably taught to say that these bromines are sp3 hybridized because they've got their 4 electron regions, and they'll minimize repulsion by taking on full hybridization. So it's, I'm not going to argue that maybe it's not a p orbital and it should be drawn as an sp3 orbital, but that sp3 orbital would also have 2 lobes, one shaded, one unshaded, that has overlap with the pi star orbital. So in one instance, the alkene is giving its electrons to the bromine sigma star. Pi donating to sigma star, breaking the bromine-bromine bond, and kind of breaking the carbon-carbon double bond. And at the same time, a lone pair in a p orbital is being donated into pi star, confirming the breaking of that orbital. And now these electrons create a carbon-bromine bond, and these electrons create a carbon-bromine bond, so that both carbons can be bonded to the bromine. It's heavy stuff, but it is the explanation behind chemical reactions.
So if you had an alkyne, would the 2 pi bonds be of equivalent energy?
Yes.
Okay.
We call them degenerate. And I've never quite understood that because in all other contexts, degenerate means like delinquent, I think, which I don't understand. But there it just means equal energy.
So it's not due to energy which one will get broken or formed first?
Correct.
Okay.
With an alkyne or any triple bond, it's not about energy which pi bond breaks, it's only about orientation, because those 2 pi bonds are perpendicular to each other. So if your electrophile or nucleophile rams onto your triple bond, it's going to hit one or the other, and that's the deciding factor.
That's why they're degenerate, because it's up to chance, not in order.
Is that what degenerate means? Like, you weren't smart, you didn't plan, you left it to chance? I don't know.
Yeah, it's just like
When I was in college, a friend of mine left a note while I was away from studying, and she said, "Have a great weekend, you degenerate." And I didn't get it. I had to Google it. I thought she was saying I'm equal in energy to her.
that's so nice.
I know. Thank you, Selena.
Just calling you a troublemaker.
Absolutely. Okay, I want to expand this. I want to take the MO diagram that we just built for my carbon-carbon double bond, and I'm going to add another sp2 carbon, and I'm going to create an allylic system. Anybody remember what allylic means?
One away from an alkene.
Good. Some sort of connection next to an alkene. Now I'm gonna ignore, yeah,
So that pi to sigma star one,
yeah,
you're going from like this HOMO to that top one, to the one above the LUMO.
on bromine,
Yes.
not on. So it's bromine, Br2's sigma star, not the alkene's sigma star.
So those electrons are going to break something,
These pi electrons are breaking bromine's sigma bond.
but they're keeping the electrons with bromine.
They're sharing their electrons with bromine. All right, I'm gonna ignore our sigma orbitals because remember the sigma orbital and the sigma star orbital didn't even play any role here on our alkene because the sigma bond never broke. So when we look at this allylic system, we're gonna remove ourselves from the sigma bonds. We're gonna pay attention just to the pi bonds, the pi orbitals, excuse me. So remember, I've got pi star and pi, and now I'm introducing something that would have fallen right into the middle of pi star and pi, which is just a p orbital. And now the MO diagrams get kind of fun and a little bit weird when you get all of these different ways that they can combine. Total constructive, total destructive, and kind of right in the middle. Now we can't really call them pi and pi star because we've got multiple pi orbitals. So we just number them from lowest energy to highest. We'll call this pi 1, pi 2, pi 3. And we're going to draw out pi 1, pi 2, and pi 3. But before we do, I want to notice something that we saw here with pi and pi star. These two orbitals were in phase, no nodes separating them, and then they became out of phase, one node separating them. Every time you go up in energy with molecular orbitals, you add a node. So these will have increasing nodes from 0 to 1 less than the number of orbitals that you put in. So n minus 1, if you will. For our case, this is going to be 2. For this specific example, there will be 2 nodes. So pi 1, just take 3 p orbitals and draw them next to each other in phase. Do you know what? I'm sorry. I'll organize these by energy as well. So we'll put pi 3 at the top. To show pi 1, we draw 3 p orbitals next to each other, all in phase, lowest energy orbital. To draw pi 3, we draw 3 orbitals next to each other, all out of phase with each other. Notice that the nodes run between the nuclei. And notice that the nodes are fairly symmetric in the structure. How many nodes in pi 2? 1. Where will it fall if it falls symmetric? No, because they actually already have an angular node there. Good point though. Because they got that top lobe, bottom lobe. It's gonna fall right down the middle. And a node that falls down the middle of 3 atoms means that one of the atoms doesn't experience the orbital. I'm going to draw the nuclei so that you guys can see what I'm talking about. Here's a nucleus, nucleus, nucleus. Here's a nucleus, nucleus, nucleus. Those black dots, pi 1 and pi 3, those are all nuclei. On pi 2, nucleus, nucleus, nucleus. the central atom does not experience the electron orbital. So what does this mean? Well, to understand it better, we might want to look at how many electrons we're bringing to the table. So, consider case 1. The p orbital is empty. That means that I have 2 electrons in my pi orbital, and I have 0 electrons in my p orbital. That gives me this dot structure, this bond line structure. A double bond and a carbon that lacks electrons, a positively charged carbon. That is an allylic carbocation. MO theory says that the 2 pi electrons in this system, they go into pi 1. Which atoms, 1, 2, and 3, left, center, middle, are experiencing these 2 pi electrons? All 3. So why does the bond line structure look like only the 2 atoms on the left are experiencing it? Introduce resonance. Resonance is the movement or delocalization of pi electrons. With bond line structures, it looks like movement because bond line is limited in what it can portray about a molecule. In MO theory, resonance looks like delocalization, pi electrons that span several atoms, not just 2. So we have this resonance form, and we have this resonance form, which are related to each other by a resonance arrow and an electron arrow. This looks familiar, correct? You've seen resonance depicted with electron arrows? You have, yeah. But neither of these forms are truly accurate. And so we can say that this is roughly equivalent to this 3-bodied system having a partial double bond with a delocalized positive charge. That is the resonance hybrid on the bottom. Above it are the 2 resonance forms. And I'll be honest, they both add a little bit of something, but they also both lose a little bit of something. If you look at one resonance form, you're being lied to about where the charge is. You're being lied to about the LUMO and sometimes the HOMO. It looks like on this resonance form that this carbon can accept electrons, but then we realize on this resonance form, the other carbon can accept electrons. So we can say carbon 3 and carbon 1 can both accept electrons. Does MO theory support that? Yes. MO theory says that vacant electron, that vacant orbital, that positive charge, is sitting over atoms 1 and atoms 3. So where can electrons go? They're going to go into this orbital. I'm going to say this. Case 1, P is empty. pi 2 equals LUMO. Which atoms can accept electrons? Either 1 or 3, but not atom 2. The orbital doesn't exist over atom 2. Notice that in both resonance forms, atom 2 has a pi bond. It doesn't want to accept more pi bonds. And then we look at this resonance hybrid. That misleads us into thinking that, well, maybe carbon 2 can take the electrons because this positive charge seems delocalized across the whole thing. So, MO theory provides us some context. Dot structure provides some context. There's really no good overlap between the two. All right, I want you guys to have a quick break, and then we're going to look at case 2 and case 3, where we add electrons to this allylic system, and we see what it does. Okay?
Positive charge cannot be on the center one, though.
That's correct. According to the MO diagram, the positive charge isn't, which is why the resonance hybrid is even flawed.
I thought it was because there's a hydrogen coming off it. So if it has a double bond, a single bond, and a hydrogen, then it has 4 bonds.
Yeah, you are right.
Is that the same thing as saying the resonance doesn't allow it, or the shell's not there?
So MO theory isn't saying that the central carbon can't have an electron orbital because it already has too many bonds. MO theory is saying there is a node that falls over atom 2. So, conveniently, atom 2 cannot have the positive charge. Atom 2 is satisfied.
I'm kind of curious, what about like when you shift do like the carbocation shift, the hydride shift? Wouldn't
That's
that-
different. That's not an allylic system. A hydride shift is more like a sigma orbital overlapping with a sigma star orbital. No, excuse me. It's more like a sigma orbital overlapping with a p orbital, and the electrons moving. Because remember, a hydride shift happens when you have a carbocation. So it has a p orbital that is unfilled. Adjacent to it, you would have a sigma orbital. And that sigma orbital would actually look like this, because it's the overlap of S from hydrogen and hybridized from carbon. And that looks a little bit like a weird p orbital. So if you get the overlap between this sigma CH and empty p, then the electrons just bleed over.
Okay, that actually makes sense. It's like, because you still have the double bond there. That makes sense with it. Okay.
And the double bond isn't moving. The double bond is across all 3 atoms. Lewis dot structure just can't show that. It can't show that and also show that it's atoms 1 and 3 that are electrophilic.
I guess what I'm thinking is like the double bond is always present. So that's why, okay.
Right.
So that's why the positive charge is going on the middle one. Okay.
MO theory to me is so cool.
It is pretty cool.
How many bonds can hydrogen make? Just 1. There is a compound called diborane. It's what happens when boron borane BH3 dimerizes with itself. And you'll notice that this has 2 bonds to hydrogen. It results because of the molecular orbitals of borane. So borane is BH3, and it's planar. The boron has an unoccupied p orbital, according to valence bond theory. But when you use molecular orbital theory to build the molecular orbitals of borane, it allows for the hydrogens to actually bond to both of the borons at the same time. It's, to my knowledge, the only time hydrogen bonds twice, stably. I wish I actually, maybe I can find the molecular orbital diagram for it, because it's beautiful. It is one of the only times hydrogen is partial negative. You're right. MO diagram of diborane.
So like if the bonds were to break, the electrons would go to hydrogen.
That's correct. Yeah, the bonds belong to hydrogen by like 0.1 electronegativity difference. So hydrogen owns those electrons less than carbon owns the electrons of a CH bond.
Then you could get hydrogen sodium.
Sodium hydride, NaH, which is Na plus H minus, does exist. I'd have to bring my notes because I feel like these are not doing it justice.
So does each pi level mean 3 possible bond outcomes? Or are these all there at the same time?
So the math always exists. But as you can see, in case 1, only one of the math equations is occupied. And this is something that I always struggled with when talking about MO theory is how does it exist if nothing's in it? It's a mathematical equation. So you can write a mathematical equation that describes a wave in the ocean. There doesn't need to be a wave in the ocean that obeys it. I would say actually that's a lot of what digital things are. It's just, oh, I'm sorry, I thought you were looking at it. And it doesn't matter. I didn't find anything useful. Anyways, for those of you that were gone, this is diborane. And what's wrong about it?
Hydrogen has 2 bonds going to it.
Yeah. We know that hydrogen can only make 1 bond, but MO theory says that's stupid. Watch this. Or in the words of a Wisconsinite, hold my beer. And it's only because of MO theory. It's because of the molecular orbitals of borane overlapping with the other molecular orbitals of a second borane that it can dimerize through the hydrogens. All right, I want to move through these a little bit quicker. So case 2. The p orbital is a radical. The electrons that we get now have a filled pi 1 and a half-filled pi 2. And so we get these 2 resonance forms. One that says carbon 3 has the radical, one that says carbon 4 has the radical, and that's because pi 2 is a molecular orbital that does not sit over the central atom. So only the ends of that allylic system are radicals. And again, we get the hybrid form of this, which again is a little silly because can the central atom be there? But at least we recognize the pi bond is not localized, it's delocalized. And then we have case 3, which is where the p orbital has a pair of electrons, a lone pair of electrons to bring. Which means now pi 1 and pi 2 become filled with electrons. And I get these two resonance forms where, again, only the allylic atoms, 1 and 3, have this lone pair. The central atom doesn't experience this lone pair because that lone pair is occupying pi 2. And then, of course, we can draw this resonance hybrid. I want you guys to recognize I'm saying is approximately equal to because it's still limited. It still has its shortfalls. Now the application of this. Those of you that were in my summer class, and maybe those of you that were even in my spring class, you might not have really seen the answer here. If you take an alkene molecule, and I'm actually gonna do something here. I'm gonna make this 3-methyl cyclohexene. If I react this with Br2 and light, yeah, that's one of the reactions I never put on there, on that review sheet. Shoot. Cyclopentene. 3-methyl cyclopentene. First of all, the light cracks bromine into 2 radicals. One of those radicals takes a hydrogen away from this system. Where is the easiest hydrogen to take away?
The edge of the methyl? End of the methyl?
No, that primary carbon is not. That primary carbon is actually the least stable hydrogen to take because it creates the least stable radical. Tertiary would be a good guess because the most substituted radical is the most stable unless there is a position that is resonance stabilized. And how do you get something resonance stabilized? You make it allylic. So either of these positions that are adjacent to the alkene are allylic. So I'm not going to show the final product yet. I'm going to show an intermediate that forms. Would you guys agree that either of these positions are identical? Doesn't matter which one I choose. Is this the only molecule? Is this the only structure of this compound? Allylic radicals have resonance. So this must have a resonance form. Now, to be fair, these two resonance forms up here on this propenyl radical are basically identical. But let's draw the resonance form for this structure and see if it's identical. You're not going to be doing a lot of arrow pushing with radicals this semester, but if you want a refresher, 1 radical electron, 1/2 arrow. Pi bond breaks into a radical electron and a radical electron. So now I get a second resonance form where the pi bond has shifted and the radical has shifted. Are these the same resonance structure, like the propenal radical? Jacob, can you describe the difference?
It would just be different compounds because the relation between the alkene and the methyl group is different.
Absolutely. We said this was 1, 2, 3. I said it was 3. Sorry. I said it was 3-methyl cyclopentene, but it's 4-methyl cyclopentene. Whereas here, it's 1, 2, 3-methyl cyclopentene. So the relationship between methyl and the alkene is different. That means that when these react, I'm able to get 2 different products. When that second bromine radical comes down and terminates the reaction, I get 1 bromine where the radical originally formed. 3-bromo, 4-methyl cyclopentene. And I get a bromine where the radical was in resonance. 3-bromo, 5-methyl cyclopentene. So if you create an allylic cation, an allylic radical, an allylic anion, you have the potential of a reaction happening at 2 different spots because of a molecular orbital that says the reactivity is not localized to 1 carbon. When this radical formed, it did not form this structure. It formed this molecular orbital. Immediately upon formation, 2 possible products are now allowed. That's the power of MO theory. Someone had their hand up?
Why does the pi bond go up? Can it go anywhere?
It's in resonance with the radical. That's why it went up, because the radical was up.
Why is the radical go to the top? Why doesn't it go one away on the bottom?
The radical could have been on the bottom. Both of those positions were identical to each other, so I just picked one.
So it could end up anywhere. But
No, the radical will form allylic to the alkene, but those 2 positions are identical to each other. So I just drew it one way. If you flip this molecule over,
if it's chiral.
if it's chiral, it's a different situation. We'll talk about that later.
But what, couldn't it end up on all 4 if it's chiral? The bromine?
Yes, this is a chiral molecule in the end. So you have stereoisomers that are produced. You're right. Right now, I'm just focusing on the resonance of it and the MO theory application of it. Questions so far? Isn't it so good? Don't you just love the math equations that look like shapes and tell you that things can move in ways that you can't draw? This is what I want you guys to take away from this. Just because you can draw it doesn't mean you can really draw it. You have to accept the fact that there is more going on than what you see. And you've got to remember that, and you've got to practice it. Although, to be fair, this stuff doesn't really have direct application practice, so that can feel a bit tricky. Keeping on the topic of resonance, which again follows MO theory, so think about how this applies. I want to take a minute to look at factors that affect resonance, or resonance contribution. In a resonance form, what things contribute to that resonance form being a major contributor, looking like the structure the most? That's kind of what we're saying. What stabilizes one specific resonance form?
I think I need you to rephrase that question. It's way too
That's fair.
convoluted.
Yep, and a lot of words. What stabilizes a resonance form the most?
Like a heteroatom that's more comfortable with a negative charge, like oxygen compared to carbon or something.
Sure. Putting a negative charge on a more electronegative atom.
Is this where caryo comes into play?
Not yet. Nope. Caryo will come in with acids. Resonance is the R in caryo.
That's right.
Yep.
Minimal charge.
Minimum charge. A resonance form that has the least amount of charge possible is a more stable resonance form.
A big molecule?
No, size of the molecule doesn't quite matter.
Conjugation.
Conjugation's a good word. Anybody got a definition for conjugation? It's not a contributing factor, but it's something we should touch on.
Is that when there's multiple alleles in a system?
Not necessarily. The 3 p orbitals, that's why I didn't erase it. The 3 p orbitals in the allylic system are conjugated. When you get to a 4-carbon system, or a 5-carbon system, or a 6-carbon system, or heteroatoms, etc., and there are huge molecules that are conjugated. What you're saying with conjugation is an uninterrupted series of p orbitals.
I mean, is it fair to say it almost forms like this pipeline, theoretically, that an electron could flow through?
100%.
Okay.
For example, metals are basically the most conjugated you can get, and you create a sea of electrons. Metals actually go from just having their atomic orbitals, and once you start bonding them next to each other, this starts happening, MO theory starts happening, and their atomic orbital gaps become molecular orbital gaps that get smaller and smaller until you have enough metals next to each other that there is no gap between their molecular orbitals. And you can take electrons in the HOMO, and they just flow into the LUMO, and they flow away with even the smallest amount of energy. Heat something up, and that metal is now conducting electricity. Yeah? So conjugation gives resonance. Resonance doesn't work without conjugation, but we use conjugation in another sense as well. We use conjugation in the term of acids and bases. The conjugate acid, the conjugate base, which means they're related to each other. Here, conjugation means their p orbitals are relating to each other. Uninterrupted series of p orbitals. Resonance is the movement or delocalization of pi electrons, so you need those p orbitals to do it until you get to metals, and then their d orbitals can overlap like and create a pi bond. When I was in graduate school, actually this would be a great time to show this. I worked on developing electrically conductive metal organic frameworks. And so this molecule on the right was designed to be fully conjugated. The nitrogens conjugated to the aromatic structures, the aromatic structures conjugated to one another, and then you could place a copper metal node by each of those pairs of amines, each of those pairs of nitrogen groups. And copper's d orbitals would be able to conjugate to the conjugated system through the nitrogens. And then you could push electricity in to like one end of this crystal, and it would flow through this molecule, through the copper, to the next molecule, to the next copper, to the next molecule, through this framework of metal, organic, metal, organic, metal, organic, only because they were fully conjugated with their p and d orbitals,
So is electrical current just conjugation?
essentially. You want to talk about semiconductors? They are not perfectly conjugated, and so they've got a band gap, which means in order to get electrons to move, you need to overcome a minimum threshold. But the only way that you can get that threshold down to a reasonable amount, such that light from the sun can cause that to happen, you need to conjugate them in these giant frameworks. Usually metals and semiconductors, they have like metalloids, silicon, germanium, stuff like that, boron. And so they are conjugated. They're not metal organic frameworks, they're more like metalloid frameworks. But it is endless conjugation. That's the goal. Yeah. Cool. All right. Back to resonance. Sorry. Minimum charges is actually the number one rule. A compound that has, or a resonance form that has maximum charges is the least major resonance form.
Say that one time.
A resonance form with maximum charges is the least major, the most minor resonance form. Contributes the least to the character of the compound. Number two. Ooh, I heard some whispering. Sorry. Maximum octets comes next. You remember this well, Christina. After you have maximized octets, then you want to place the charge appropriate. There is one big instance that this seems counterintuitive. Appropriate charge placement. Appropriate charge placement means negative charge on more electronegative, positive charge on less electronegative. So let's take a small system for example. Often, but not always, resonance structures work in three, similar to the three that I've shown you here. You need 3 atoms to move pi electrons across. However, sometimes all you need is 2, and I'll give you guys some examples. This structure has a negative charge, which means the least major contributor would be when that negative charge is on the least electronegative atom. The most major when it's on the most electronegative. So let's show one resonance form where nitrogen shares electrons to form a double bond, which then pushes out a double bond onto the third atom. 1, 2, 3. Lone pair in, lone pair out. And now this oxygen can also share, this carbon can also share its lone pair with the oxygen. These 3 resonance forms are all separated by a movement across 3 atoms. 1 atom has the charge, 2 atoms have the pi bond. But I can do a resonance form that only involves 2 atoms. That usually means just making or breaking a pi bond. So I'm going to do one last resonance form where I show the original pi bond I made breaking back. Why don't you turn to the people next to you and rank these from least major contributor, least like the nature of the molecule, to most major contributor, the one that looks the most like the molecule at its lowest energy. Work with the people around you to rank these using these three rules.
Like the second last.
The last one.
Yeah, that one's
And then I think after that.
This is the one.
Yeah.
And then the one for nature.
Keep drawing. Finish your drawing. Please confirm.
I think you have some idea. Would you agree that all four of those structures have the same carbon chain? How many carbons in that molecule? Yeah, I agree. And a nitrogen group and an oxygen group, right? Now the only thing that's changing is the placement of the pi electrons. And that's what resonance is. It's a delocalization, which looks like a movement, but MO theory says it's not a movement. MO theory says it's a delocalization. The electrons are never in those specific spots necessarily. Mhm. Now, if you follow stability, contribution to the molecule, which of these resonance forms does the molecule actually look like the most? Yeah. What's the most stable form? And what's the least stable form? So, least stable, actually, Courtney, do you want to give a hand at the least stable?
The least stable.
Uh-huh.
The one it doesn't want to be.
So we want to minimize charge, we want to maximize octets, and then we want to have appropriate charge placement. One of these breaks rule number one.
I just was considering only the last one looked like maybe it was the most stable, so I don't.
The most
have any
stable,
idea.
because of all the charges?
Maybe just because the positive and the negative are next to each other.
That is something that we want to avoid. We want to minimize charges.
Okay, so opposite.
Good.
We don't want to look like that.
This is our least major contributor. This is our least stable form. We don't want that positive and negative. Because if we have a positive and negative next to each other, we probably could just have them bond and not have any charge. And that's what we want to do. Nayura, what's our most stable form?
I said it would be the one with the third one.
Why?
Because the oxygen is the one holding the negative charge.
Most appropriate charge placement. Exactly. Most electronegative atom here holding the negative charge. Now, how would you go about ranking 1 and 2? Cameron?
Phenomenal question. I would say the second one is probably the more stable of the two because the electron pushing arrow takes the negative charge to the oxygen
Okay.
where it wants to be.
I would say maybe ignore the arrows because in this form, oxygen doesn't have them, carbon does. And in this form, nitrogen has them. So that's what I want you to compare. Compare when carbon and when nitrogen has them. Does this follow minimum charges? Does it follow maximizing octets? Then it must follow electronegativity, appropriate charge placement. So Cameron, can you tell me which is more electronegative? Good.
So
So-
the top one's more stable.
This becomes our second most stable. This becomes our third least stable. Or third.
You were just showing how they relate to each other with the arrows.
That's correct. I was showing you how the electrons are moving. But they're not moving. Russ?
So, I guess I'm maybe forgetting my electronegativity here, but oxygen is more electronegative than nitrogen.
That's right.
Which is why that's more stable.
That's
It's more of the natural habitat for the negative charge.
Good. This order. Yep. All right, now I want to flip it a little bit. I'm going to have a carbon with a positive charge. I think I'm doing something wrong. I'm sorry. I'm doing something wrong, but I can't seem to figure out what. All right, we're gonna go like this. No, I'm changing it one more time. I apologize. That's a weird compound. Doesn't look very stable. I wouldn't advise working with it. The charge is going to be consistent in this one. So we're not going to be looking to minimize formal charge. You guys noticed that here we never actually dealt with maximum octets. They all had full octets. Here, I can show a resonance form where nitrogen shares a lone pair and makes a double bond to the carbon. Or oxygen can make that lone pair and double bond to the carbon. I did make a mistake in that second form. So tell me, guys, tell me if you guys can spot that mistake I made. Yeah, I forgot the charge on the nitrogen. Most students look at this problem and rank it slightly incorrectly. They get 2 of them ranked correctly, and they get 1 of them drastically wrong. Because they go right to rule number 3, and they say, I will place the positive charge appropriately with the most electropositive atom, the least electronegative. Axel, what is the least electronegative atom between carbon, nitrogen, and oxygen? And I'll give you a hint. This is what the periodic table looks like, and this is how electronegativity trends. So, which of these 3 atoms, carbon, nitrogen, or oxygen, is the least electronegative? Carbon, nitrogen, or oxygen? Carbon is our least electronegative. So most people look at this problem and they say, carbon holds the positive charge the best, and like Axel said, oxygen holds the positive charge the worst. But this lacks something that the other 2 have. Octet. It does lack a pi bond, but it also lacks an octet. Carbon there only has 6 electrons around it, which means rule number 2, that first structure does not have maximum octets.
So it's maximum octets of carbon specifically, or just across the molecule?
Of every atom, but to be fair, when nitrogen has a negative charge, it has an octet. When carbon has a negative charge, it has an octet. When oxygen has a negative charge, it has an octet. Negative charges, octets. When nitrogen has a positive charge, it has an octet. When oxygen has a positive charge, it has an octet. Carbon is the odd one out, that when it has a positive charge, it lacks an octet. So it's kind of this weird thing where, yeah, maybe you could say maximum octets to carbon, because that's where it's going to happen the most. You know what? I've never said it that way, and that might be the best way to say it.
To carbon or to the most relevant atom? Because I was thinking that the one on the far left would be the more stable one because nitrogen has its full octet there.
It still has an octet here. It has it has 2 bonds to hydrogen, 2 bonds to carbon. 4 bonds is 8. And here it gets its lone pair back. So how would you compare these two?
So, I mean, practical application in the real world, that rule is going to apply to carbon most of the time.
It is mainly just carbon. Yeah. I mean, you do want maximum octets, but carbon is usually the problem child there. Lacks an octet. This is our least stable, our most minor contributor. These two have full octets. So then we go back to what Axel said earlier. Since we're only going by appropriate charge placement, and since oxygen holds positive worse than nitrogen, this is our second least contributor, and this is our major contributor. Most stable. Here's what a lot of students get mistaken here. They say appropriate charge placement means oxygen wants the charge. That's not always true. Nitrogen also likes the charge if it's a positive charge. And if there's no oxygen, nitrogen is a good electronegative choice, right? So, that's all we got to today. Next week, our game plan is I want to review acid-base concepts a little bit because we are going to see them again this semester in some new contexts. I want to review our reactions. I want you guys to take a stab at those reactions to see which ones you remember. And what I'm going to put on the board is a condensed diagram of all the reactions we saw in OCHEM 1, so that we're not doing the same thing I did in OCHEM 1, where I'm going one after the other, after the other. I also, on Tuesday, want to review some terminology. I feel like maybe we were overdue for terminology, but I want to quickly review, like, stereochemistry, chirality, regiochemistry, functional groups. I want to make sure we're all on the same page for that. So that is Tuesday. Thursday, we're going to review spectroscopy. You know, I could flip those two. We could do spectroscopy first. Maybe we do spectroscopy and some terminology Tuesday. Because I want you guys to have time to ask questions on spectroscopy, because you will see it on your unit test. Would that sound better? Do you guys feel more concerned about spectroscopy than reactions? No? It's both. Okay. All right, well, we'll feel it out. We've got a lot for next week. It's going to be a great week. So have a good weekend. Come with questions next week if you have them. Did I mess the camera up?